Is it possible that the empty space is also created by the space-time? I know it sounds crazy and you may regret for calling me to your podcast. But I'm proposing once again the following. You send the particle to what you think is a vacuum. Okay, there is nothing there. And then you have a wave function going to the vacuum, and then you make measurements and you find it only in one place. All the other places are empty. So there is nothing there. There is space and time. Is it possible that the wave function actually creates not only the particle, but also the space-time surrounding it? So collapse gives rise not only to the particle in the location, but in all the points in empty space where it could have been. And then, so here it is. Here you have particles. They interact with one another. Sorry for this silly thing.
No, that's cool.
In that nothingness. And then you have particles and the space-time around them. And once again, they interact in the nothingness, and then you have space-time around them. So what I'm proposing is that the quantum interaction precedes space-time. Space-time emerges from the interaction, whether these are photons or gravitons, or perhaps even the real particles. I'm not completely sure about that. I say that electromagnetic waves and gravity waves shape our universe. They shape our rulers. They shape our clocks by exchanging photons between them, because this is electromagnetic. And when you are talking about the universe, there are gravitational forces between them. Is it possible that what creates the empty space is just these gravitons and photons, their wave functions that actually interact with one another in the nothingness? You know, when I talk about nothingness, you see this black part.
Mm-hmm.
It is similar to the nothingness outside of the universe. You can't go out of the universe because the universe is space-time. We are bounded by this nothingness.
Right.
And I guess that this is how I would propose that space-time is emergent. And so on. Now, so this is the speed of causal connections. I now I'm not surprised that the velocity of light is always the same, no matter how I travel, because when I travel, my world line and all the force-carrying particles, whether photons or gravitons, interact with the environment. So they create the space-time between them. Now I am not surprised that when I measure the velocity of this force-carrying particles, it is invariant. And now I think that we are going to get the great reward. So mass gives rise not only to space-time curvature, but also to the bumps in the plane. So you ask whether this now is always the same. Frankly, I don't know. I would guess that every time that there is a mass, then somehow this simultaneity will change and time is moving differently in that place. This is not Schrödinger's cat, but
Right.
And now something interesting. Think about the EPR experiment or Schrödinger's cat. I think that now you have a good explanation to them when you say, and this goes to your question about whether time is simultaneous or not. When the time moves, you see that it leaves some corridors which are not filled yet.
Okay.
And these are the two corridors of the two particles. As long as you did not measure them, there is no space-time there. The moment you measure them, then the now goes and fills the gap that you have left in this corridor. I look at the Schrödinger cat, and a student many years ago asked me a question, and it was a very bright question. She said, "Why are you physicists so much bothered about Schrödinger's cat? You want to know whether it was superposed or not when the box was closed." I can show you that he was not in a superposition, because all you have to do is to make the experiment longer, say 3 days, and then open the box after 3 days. So the little event which occurs or does not occur has to occur at the beginning, and then you wait for 3 days
Right.
in the box. Then you're not going to find only a live cat or a dead cat. You're going to find a live cat, but very lean, just like this cat, very lean and angry and all droppings and so on. Or you are going to find a dead cat, but already decomposed.
Right.
So she said, why are you bothered about that? Do you agree that this is a very profound question? And my answer is that as long you see this rectangle on the left, as long as the box was sealed from the rest of the universe, there was no space-time there. The cat being superposed means that its evolution has stopped. Now, when you open the box, becoming goes back and fills it.
Uh-huh.
So actually, you're creating back the whole history of the cat. When you're opening the box, you are not only determining the cat state, but you are determining its entire history. This is very similar to John Wheeler's delay choice experiment, in which you have a photon coming from far millions of years ago, and then now by making an interference experiment or just measuring its position, you are actually choosing the kind of history that you have. But I'll be happy to talk about Wheeler's delay choice experiment another time. But actually, the idea of becoming actually tells you that many of the quantum mechanical problems can be better understood in this way. And here, before I finish, I come to the most, and then the origins of time asymmetry, all the asymmetries. There are important books by Davis and others, the physics of time asymmetry, what is the master asymmetry. So I would say that it is becoming. But now, how about, and with this I come to the conclusion, if two particles, what I propose here is that two particles interact with one another in the nothingness outside of the universe in a way that I don't know how to describe. It's beyond, you need very strong mathematical tools, and cosmologists may have it when they talk about the origin of the universe, kind of pre-state in which the universe exists, or how universes are born from one another. I'll talk about it later. But if you say that the quantum mechanical interaction occurs beyond the now, in the next moment, where there is nothing, there is no time, no space, and then space and time emerge by this interaction, Curt, you're going to get their relative positions, which means that you're going to get attraction, repulsion. They come very easily for this. They don't have a position yet. They don't have a momentum yet. It's only they interact in a very mysterious way outside of space-time. And then there is a collapse, and then the whole space-time is there. Do you understand that you can get gravitational attraction or electromagnetic attraction and also repulsion coming naturally and smoothly from these dynamics?
It's not entirely clear to me.
You have world lines. And according to relativity theory, the naive relativity theory, the world lines are just there. Past, present, future. Now we are proposing that there is a now which draws the world lines.
Uh-huh.
Okay. And I suggested that they interact with one another quantum mechanically. You see, the black realm is where this is the now. And I suggest, and out of it, it's just like out of the universe. I mean, the future is just like out of the universe.
Yes.
No events, but there is no space-time. Space-time is being created, is growing. Now, when I suggest that the wave function creates not only the particle, but the space surrounding it. Remember that in general relativity, actually, there is an interplay between mass and the space-time surrounding it. Here, I'm proposing similar thing in quantum mechanics. There is a particle, and it gives you a wave function. And as long as you did not make a measurement, it may be in many places. Then you find where the particle is, and all the other places are empty. I suggest that the collapse of the wave function, or whatever it is, gives rise not only to the particle, but to all the space where it could have been there. So the empty space is also a product of the wave function. Now, if a particle creates the space and time around it, do you understand that attraction and repulsion now, the relative positions of particles or bodies, planets, can be better understood in this way? That space-time is being curved, but the curvature of space-time is due to interactions which are outside of space-time. They are first quantum mechanical, and then when there is kind of measurement or collapse, and then there is becoming, then you have the body, whether it's a charge or mass, and it has a new relative position to the other body, to the other charge or mass, because they have created the space-time around them.
Okay, I see what you're saying. So are you saying that the filling in of space, either if it's filling it in between two particles, that's repulsion, if it's filling it in outside of the two particles, it's pushing them together?
Yes.
As you know, on Theories of Everything, we delve into some of the most reality spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.